Hello everyone, today we're going to look at uniform circular motion and specifically we are going to look at the two first equations you might come across, which I'm going to give away right away, which is that the speed of something in circular motion is 2 pi r over period, and that the centripetal acceleration is v squared over r. That's going to be where we're going to get to. Let's first of all look at a situation. And here I've got my cartoon character spinning a mass on a string above his head. The mass is clearly traveling in a circular motion. And if we were to look at this from above, we should see, obviously, a circle that looks kind of like this. And we would say that that circle, of course, would have a radius. And then if we would imagine our object to be at a certain position on that circle at any given time, we might be able to define the kinematics of this mass as having, let's go ahead and say that there's a speed. We'll call this the initial speed. And then at another given instant in time, the object might have moved on a little bit around the circle, might have moved on some given angle, and at this point there'll also be a new speed, which would be tangential to the circle, and we would call that the final velocity if we were just looking at these two instantaneous speeds. Now, what's important is that we can describe the difference between speed and velocity. So if I'm looking at just speed, then if I was to compare these two, then I would say that they are equal to each other. Because when I'm just looking at speed, I'm only interested in the magnitude. Okay, and the magnitude, if this is indeed uniform circular motion, the magnitude of the speed is going to be the same. However, if I restate these values as vectors, in other words, I call this VI and VF with regards to them being velocity vectors, and I look at the difference between VI and VF, then I have to make the statement that even though the magnitudes are the same, in other words, the speed, the value associated with these, the value associated with these vectors at the different points is the same magnitude, clearly you can see that the direction is not. So I cannot say they are equal. In other words, there must be a change in the velocity. And if there's a change in the velocity, then there must be an acceleration. If there's a change in the velocity with respect to time, there would be an acceleration. And we should recognize this equation from kinematics. So that's the first thing that's worth mentioning, and it's a very important distinction that will affect how we think about the kinematics. However, let's just peel back a little bit and think about what we could possibly measure as we're spinning this thing around our heads. Hopefully you can see that obviously I can measure the length of the string. I also might be able to time, so I might get a time value for how long it takes to do one lap, if you like. So the time it takes to go all the way around and back to here, I could time that. So the time for one cycle. Okay, so this is where we have to think about the difference here between period, so capital T, period, and we're going to define period as the time taken for one complete cycle. And that is very different to the frequency, F, the frequency. The frequency is how many cycles So the number of cycles per unit of time. And that unit of time could be seconds or minutes, kind of depends on whatever you want to use. Normally in physics, we use the unit hertz, which is a revolution or a cycle. Actually, I'm going to change that to cycle. So cycle per second. And that makes sense since second is what we normally use when we're talking about speeds. It's a standard unit. So hertz is the cycle per second. And it's important then to reflect on the relationship between period and frequency. And hopefully we can see that we've got this inverse relationship. So period is equal to 1 over f, and then f is equal to 1 over period. Okay, so if we think about first principles, first principles would be distances and times, the three-dimensional space that we live in. In kinematics, of course, if we know the distances, or if there's a change in a position, or a change in a distance, or a displacement, and that change takes time, or a change in the time, then hopefully you can see that we have a velocity or a speed, depending on whether we have a vector or not, or a direction or not. So what would be the distance? Let's assume that we come back to our circle. The distance to do a full lap. Well, hopefully you can see that the distance to do a full lap is a full circumference of a circle. So the circumference of the circle, let's just say 1 circumference, over the time taken to do that, well, that's the period, right? The period is the time taken to do 1 complete cycle. So 1 circumference over 1 period is going to give you this speed, okay? So let's just put that in. That's going to give us that speed. Now we can't say, remember, we can't say that it's velocity because the velocity is constantly changing, but we can say speed. So that gives us our equation that we saw at the very beginning. The speed of a uniform circular motion is going to be the circumference of a circle. Now remember, the circumference of a circle is 2 pi r. And the time with which it takes to do that full cycle is the period. Now, we also have this funky relationship, inverse relationship with period and frequency. So this equation could also be written as 2 pi r f, since period is the reciprocal of frequency. So this gives us enough information to talk about our key notes from our lesson. The big one to start with is that there's actually 2 ways to change velocity. There's the change in magnitude, which we typically think about, so speeding up and slowing down, but importantly now for circular motion, that we also have this change in direction. If you have a uniform speed, but a changing velocity, that must mean you have circular motion, and that is called centripetal acceleration. Okay, you have a changing velocity, but a constant speed. You must be going in a circle, and therefore you have a centripetal acceleration. Okay, this is what is the definition of uniform circular motion. That gives us our equations. We're in meters and seconds. That's important. And again, just thinking about these vectors, we importantly recognize that these vectors are tangential to the circle, and that's going to be very important as we move on to look at the acceleration. But at this point, we have enough information to talk about an example question. Go ahead and quickly solve this example. So we have a centrifuge spinning at 3,600 revolutions per minute. I'm paying attention to the units because minutes is not something that we're used to using as a unit, so I'm going to have to pay attention to that. And also diameter. My equations have radius, so I know a couple of things here. I already know that I'm going to have to go from minutes to seconds. I'm also going to have to go from diameters to radius. Hopefully those are pretty simple. And let's go ahead and do that right away with my 3,600 revolutions per minute. So 3,600 revolutions per 1 minute. Now this is cycles per unit of time. So this is a frequency. So that's also important to mention. That's a frequency of 3,600 revolutions per minute. Let's go ahead and convert that to seconds, which is what I'm going to need if I'm going to talk about speeds or if I'm going to use my equations. So let's go ahead and say that 1 minute is equal to 60 seconds, and then I can do my unit cancellation, and now I'm in revolutions per second. So if I do the arithmetic, I get 3,600 divided by 60, well that is 60, and this is revolutions per second. Well, a better way of saying revolutions per second is to say hertz. So this is 60 hertz, and this is a frequency value. Okay, next thing to note is that the diameter is obviously going to be equal to 2 radiuses. So I've got to make sure I pay attention to that as well. I'm given the speeds in meters per second, and so I can use my speed is equal to 2 pi r, and I'm going to use my 2 pi r f equation because I've got the frequency. So plugging the numbers in, I'm solving for r, noting that if I solve for r, I'm going to have to do an extra step to get to the diameter. So the r is equal to the speed divided by 2 pi f. Okay, and I can plug those values in, and I get the value of 0.22549 something. That's going to be meters. Now, that's my radius. So 2r is equal to d. So I'm going to have to multiply this value by 2, which gives me a d, which is what I'm looking for, of 0.45, and I'm going to go to 2 sig figs because I've got 2 sig figs in my question. So 2 sig figs, and that's meters. So my diameter of the centrifuge is 45 centimeters. That seems reasonable to me, since any normal sort of centrifuge would be sort of desk size. So I haven't got like ridiculous values here. That makes sense to me. Okay, so we've talked about the speed equation. Let's look at the centripetal acceleration equation. So we'll go back to our circle. Here we go. As we'd previously mentioned, we can imagine that at a certain point in time, there would be a velocity vector here. We'll call that initial. And then, of course, with a radius here. And then at another given point in time, there would be a second or a final velocity vector right here. And if we were to imagine, obviously there's an angle in here, but if we were to imagine that this time interval between these two positions is infinitesimally small, so it's just a tiny sort of calculus nudge onwards. If we imagine that this is infinitely small, we can go ahead and just ignore this curve. We're going to ignore the curvy part of the circle, and we're going to turn the arc into just a triangle. Okay, so you have to kind of imagine that we can do that as an assumption. And we've got a radius, obviously, on either side. And this yellow bar, this is going to represent, this is going to represent a change in the position. So I'm just going to call that delta D. Changing the position from here to now here. Okay, obviously the speed has not changed, but the velocity has. Okay, so if we change this into a little triangle with sort of an equal triangle on each side, we can actually start to represent this as a triangle like this. And this is going to be important. So I'm going to go ahead and just state this to be, let's call this triangle 1. Okay, there's triangle 1. And I'm just going to go ahead and say that this is R. So this side here is R. And the base, this base, we'll call this base 1. So actually we'll call this side 1. There we go. And side 1 is equal to that radius. Okay, happy. Now, the next thing we're going to do is play around with our red vectors, the VI and the VF. So what I'm going to do is I'm going to just state that an acceleration is VF minus VI over a time. Okay, well, if I look at my VF and my VI, I'm actually going to replicate this algebra with my vectors. So I'm going to take my VF, this guy here, which is this vector here. Let's recreate that over on this side of the page. Let's go ahead and put that there. Hopefully that looks similar to the VF that I originally drew. So it starts there, it goes to there. And then I'm going to subtract VI. So in other words, I need the opposite of my positive VI. I need the anti-parallel version of VI. I need that negative VI. So I'm going to represent the negative VI as the same parallel direction, except going the anti-way, the other way. So in other words, it's going to be going down. So this VI is going up. The negative VI of this vector will be going down. Okay, so I'm just going to draw that on tail to tip, just like we would normally do with a vector addition diagram. So I'm going to come down to here. Okay, so this is my negative VI. Okay, now this next bit's really cool because obviously now when we've got this change, this is a change in the velocity. So these two vectors added together as a resultant give me the delta V over a time interval, which is my acceleration. So this green arrow now represents the acceleration in a circle. And if I come back to this origin point, which is the tail of the VF, that would be here, the direction of this acceleration is, surprise, surprise, it's to the middle. So I'm going to call that acceleration centripetal, and it's pointing towards the middle. It's center seeking. I'm going to write that on there. Center seeking. Okay, the acceleration is center seeking, and it wouldn't matter where I did this on the triangle, that green dotted arrow, that acceleration centripetal would always be pointing to the middle. Okay, here's the other thing that's really cool. This angle in here, this theta, is the same as the other theta. Okay, so let's go ahead and label these theta 1, theta 2, and we can say that theta 1 equals theta 2. So these are now two different triangles. The sides of these triangles are different, or we can assume they're different. One of the sides is the radius of the circle, and the other side is the speed, the magnitude of the vector, which is speed. The angles are the same. And so this is where we can use geometry to get our derivation. Okay, so in other words, let's label it. I've got triangle 1 over here. Now this is triangle 2, with the green dotted line being the base. So let's go ahead and add triangle 2 onto triangle 1, and it's going to look a little bit like this. First of all, let's put the angle in. So that theta, remember, is the same of both of these angles here. And we've got side 1 labeled. Side 1 from, remember, our triangle 1 is labeled. And now I'm just going to add on, just to show you that we can just go down like this and add on I guess, a secondary triangle. This time it's triangle 2. So the side of triangle 2 is the velocity. Okay, that's triangle 2. And the base would be, this is base 2. Base 2 is the delta velocity, delta speed, the change in that speed there, or the change in the velocity. Okay, so why are we doing all that? Well, we can say, based on triangle laws, that if you've got triangle 1 here, and you've got another triangle, let's call it triangle 2 here, and they've got the same angle, you can make the case that base 1 over side 1 is equal to base 2 over side 2. It's a nice little ratio that just works. Feel free to go and check those numbers if you want to. It's easy to prove. But now that we've done that, we can now replace the base and the sides with the base and the sides from our 2 original triangles. So let's go ahead and do that. Here we go. This is the fun part. Base 1 was, remember, it was that yellow line. So let's just bring that back in. It's this yellow line, which is the change in the position. Okay, so let's put that in. Let's go ahead and do that. So base 1 is the change in the position. Side 1, well, side 1 from our triangles was the radius. Okay. Base 2, well, base 2, that's our delta V. Okay, so let's go ahead and put that in. So that's delta V. And side 2 is simply our sides here, which would be the speed, just on the magnitude, so just V. Okay, so now we're starting to have a little algebraic relationship that might be related to our equation. Let's keep going. The other thing to remember, I'm going to introduce this now, is that, of course, whenever you have a speed, you're going to have a delta D over, of course, a delta T. And so if you have delta D, which is what we have right here, delta D is equal to V delta T. So I'm going to replace that. So I'm going to say that V delta T is over R is equal to delta V over V. Okay, now we're going to do a little rearranging. Let's just move everything out of the way here. Move this up. Do some rearranging. I'm going to say that, or the other thing to say is that acceleration, of course, is delta V over T. Okay, so I'm going to try and rearrange this equation to get a delta V over delta T. So a little bit of rearranging. I've got my delta T here, so I'm going to divide both sides of this equation by delta T to get rid of it on the left and bring it in on the right. So that leaves me with V is delta V over V delta T. This, of course, being still over R. And this is where we can identify that acceleration. This is now, that bit there is acceleration. So I'm just going to get rid of that and say now that I've got, let's move some of this stuff up out the way. I've now got an equation where I can say, here we go, this is the last little bit. I can say that the acceleration centripetal is V, and I'm going to now multiply both sides of the equation by V to get rid of it, which means I multiply V by V, which is the V squared, and of course that's all over R. Beautiful. Nice little geometric proof of the centripetal acceleration equation. Of course, the only thing left to do here would be to prove the alternative, which is where we just simply insert our 2 pi r over t equation into v, and that would give us the other equation for centripetal acceleration, which is 4 pi squared r over t squared. And feel free to do that yourselves. You can just plug this in for v, and you'll get that equation easily. Okay. And so we have our final notes from our workbook. We have our two equations that we've previously stated, and we have some statements that we've also mentioned already, that the acceleration, the centripetal acceleration, is always center seeking, and you can see that on this diagram. If the velocity vectors are tangential, then the acceleration is 90 degrees center seeking to that velocity vector. So it's always perpendicular. Okay, so that sets us up for our final example. Next set of rules. So here we go, nice and easy, a little bit of a ratio question. So again, we have a centripetal acceleration that's given. So here's the 12 meters per second squared. That's our centripetal acceleration that's given. And what we're going to do is triple the speed. So the speed is going to be increased by a factor of 3, and the radius is going to be increased by a factor of 2. The question is, what is the new acceleration centripetal? Well, since we've got velocity and radius, we are going to go ahead and use our v squared over r equation. And what we're going to do here is insert these ratios into our equation. So speed is multiplied by a factor of 3. And what's important here is that you can recognize that the 3 is associated with the speed. Therefore, the 3 needs to be squared. The function is applied to the value. And then obviously the radius is just sitting at the bottom by itself, so that's just going to be 2. So the ratio increase of our acceleration centripetal is 3 squared over 2, which is 9 over 2, which is a factor, an increased factor of 4.5. And so we can take our original value, our 12 meters per second squared value, and apply the increased factor of 4.5, and that's going to give us a new acceleration centripetal, which is 54 meters per second squared. And I'm just checking, yep, 2 significant figures. We are good to go.